Good day, sir. Please allow me to introduce myself first. I'm Ong Tun Yao and I'm going to start my presentation with a blessed smile. So this assignment is divided into two parts. The first part will be the simulation on a cantilever beam with 2 rows and 10 columns machine. So the first element that we are going to simulate is Q4 element, and the next three would be the CST elements with different types of patterns. So there are 3 types: type 1, type 2 and type 3. So the material for the beam is ASTM Air36 steel with a dimension of 100 mm times 20 mm times 5 mm. So about the fixture, we are applying a fixed support at one end of the beam, while the free end is loaded with a force of 2000 Newton. Overall, all the simulations are quite accurate because the stress seems to concentrate at the desired region, which is at the fixed end where the deformation is not allowed. So over there, the stress is the maximum with a zero displacement. On the other hand, the free end experiences the maximum displacement with a minimum stress over there because the region is allowed to be deformed. As you can see in the figure, the beam experiences 2 types of stress at the fixed end. So the stress are compressive and tensile stress. So these stress are of the same magnitude but on the opposite region from the neutral axis. So this is the tabulations of all the simulation results. So we use the theoretical value calculated from the beam theory to verify the accuracy of the simulation results by determining the percentage difference of all the results from the theory for the displacement and stress value. So what can we interpret from the tables? So we can see that Q4 element has the lowest percentage difference, or we can say highest accuracy from the theoretical value compared to all the other CST elements with different types of pattern, because Q4 elements is using 4 nodes instead of 3 nodes in the CST elements. So among the CST elements, right, the accuracy increases from type 1 to type 3. What we can say that is different type of patterns for the CST elements contribute to different stress and displacement distribution along the cantilever beam. However, the results are not that reliable because we can see from tables each of the data, the percentage difference is over 5%, and some of them goes up above 10%. This may be due to the stiffness of the linear elements. In this case, we are using quad 4 and triad 3 in modeling the cantilever beam, so it contributes to a huge increment of the percentage difference. Alright, so let's move on to the next task, which is basically a simplification of a model by using symmetry feature. So we cut the model into 4 parts and we take a quarter of it and mesh it with different sizes of elements. So for the stress concentration region, we use a smaller Q4 elements, while for the part that is not crucial, we use a bigger size. And the transit region, we use CST elements. So like the previous task, we are using ASTM Air36 steel. However, unlike the previous task, we are using English unit here, and we are using a thickness of 0.005 inch. So all the material properties, we convert them into English unit to be inserted into the LISA software. So yeah, this is the simplified model created in LISA 8.0 software. So here's the problem. We are not sure about where to apply the fixture and which fixture should we apply. So let's try with some trials and errors. Okay, the first trials, we apply 2 fixed supports, one at the left end of the model and the another one on the top of the model. while on the right end we apply a force of 200 lb. But it's quite disappointing because the stress seems like not concentrating at the region that we want. So it's okay, so we change the fixture. We apply two forces at both ends of the model without the fixed support on the top. The stress seems to concentrate at the desired region, but then the displacement is too large and it's not logical. So never mind, we try the next combination of fixture. We add on one more fixed support on top of the model. From the simulations, we can see that all the stress and displacement value are quite satisfying, and yeah, this is what we want. And so we use the third combination of fixture. So this is the stress and displacement distribution by using the third combination of fixtures. So what can we interpret from the figures? We see that the maximum stress value is in between yield strength and ultimate strength. So when the load is removed, the model will undergo plastic deformation, and this deformation causes a permanent elongation on the model. However, there's no structural failure to be expected there because the maximum stress value is still lower than the ultimate strength. How can we know that the simulation results are correct? So we need to verify it. How do we verify it? We use SolidWorks 2018 because it's more user friendly. So other than verifying the simulation results, we also can learn that how close are the simulation results produced by two different software. So there's kind of an extra knowledge to be learned here. So because we are using two different types of FES software, so we must, and because they are using different solver, so tolerance is given for the percentage difference. And okay, so the percentage difference, although is above 5%, is still considered as accurate because of the tolerance given. There's percentage difference above 5% because of the different solver that I said just now, also due to some meshing differences between the model created in Lisa and SolidWorks. And we are simulating different types of model in both software. Like Lisa is simulating a quarter of the full model, while SolidWorks is simulating a full model. So there are some differences over there. Overall, the simulations are quite successful because of the acceptable percentage difference. So yeah, thank you, sir, for listening to my presentation, and goodbye, sir. Thank you.